About Gaussian processes, and we had looked at some of the basics. Now I'll walk over a notebook that I've created, which will specifically be showing how to implement or use GPy, which is a very popular Gaussian process library. And we're going to be looking at some of the concepts again, which we have already studied. Okay, so let's firstly, I'd like to put a disclaimer that most of this notebook that I'm showing has been borrowed from a lab from a summer school for Gaussian processes. It's a very good summer school called Gaussian Process Summer School. So you should look at the linked material over here. So firstly, we're going to be talking about kernels, and we'll be seeing how to visualize kernels and how to look at the different parameters. The first kernel or the most popular kernel that we'll be looking at is called the RBF kernel, the radial basis function, whose formula which we had looked at in the previous lecture is given by, for a two set of input x and x prime, it is given by sigma square epsilon minus x prime whole square divided by 2l square. Now this is given for a one-dimensional case. If we have to modify this formula for two-dimensional case, then we just replace this with the Euclidean distance between x and x prime in the 2D case, and square of the Euclidean distance basically. And it also has a parameter 2l squared. Right? So I've created a kernel in GPy, which is the RBF kernel, and this is with all the default parameters, and this is for the 1D case, right? So we can just look at how this kernel looks like. It has got its parameters where the variance and the length scale are default to be 1. So sigma and L are default set to be 1. Now what we'll do is to try and visualize this kernel, right? So if you've noticed, this gives us, so if you remember, we were using the kernel function to create the covariance matrix, or this is basically telling us how related two points are, right? So what we'll be doing is to, in this plot, we are plotting plotting this kernel function with the input, one of them being 0, the other being the range of x's going from -4 to +4, right? So what this is effectively telling us is that points which are close to 0, since one of a point is 0, so if two points are very close, then the covariance between them would be very high. And so the evaluation of the kernel function would be very high, and the corresponding covariance matrix that we create will have a high correlation between these two terms. And then as we keep on going further away from 0, then the kernel function evaluation turns out to be smaller and smaller and tending towards 0 finally, right? So one of the parameter that we had in this function is this parameter L. So I'll now be varying the L parameter, and I'll show how the kernel function will change. Before I show that, could you think about what would be the impact of increasing L? Okay, so I'm going to be varying the length scales from 0.05, 0.25, 0.5, 1, 2, and 4. And I'll be using the inbuilt animation tool from Matplotlib, and I'll be converting that into an HTML, so JavaScript based animation. And I'll be showing you for different length scales. Everything else is the same as in the previous setting. We are plotting the the kernel function evaluation between 0 and x, where x is varying from -4 to +4. Right. So with length scale 0.05, this is how the kernel function evaluation looks. It is very sharp and very pointed, which means that only if the points are very close to each other, then there is some relation between them, and the relation between these 2 points falls off very quickly. But if we change the length scale to 0.25, we see that the length scale has the effect that now 2 points slightly further in space are also related, If we increase the length scale to 0.5, 1, 2, you're seeing that how this distribution is becoming more spread out. So with length scale equal to 2, even the kernel function evaluation between 0 and 2 evaluates to something close to 0.6, which means that the point x equal to 2 and x equal to 0 are still correlated based on this kernel function. But if we were to go back and look at length scale equal to 0.5, then between 2 and 0, the function evaluation is 0. So there is no correlation between x equal to 0 and x equal to 2 at this length scale, right? The other parameter was the variance. So let's try and see what plotting and changing variance would look like. So in the first case, so I've kept the length scale to be 1. So I've just initialized the kernel. I'm just varying the variance of this function, of this kernel function, and the variances I'm varying in this range 0.1, 0.01 to 4. And what I'm showing is, in the first case, the variance is very, very small. So you can hardly see any variance. And if you notice, if we keep on increasing the amplitude, if you keep on increasing the variance, then the amplitude changes. So that is the role of variance. So this is the, so you go back to the formula. Then, so what this does is, by increasing sigma, you are effectively increasing the overall amplitude, right? All of the other things remaining constant. So the alternate way to understand the covariance matrix and the kernel function is to evaluate the kernel function on all pairs of points, on many pairs of points, right? So in this case, what I'm doing is to plot the covariance function, the matrix, which is created by pairwise applying the kernel function from all points ranging from -4 to 4, right? So this ends up creating a matrix, something like the following, which is the covariance matrix. If you notice that there is the diagonal entries are all 1, which means, as you would expect, the covariance function evaluated between the x and x is 1. As you move further away from the diagonal, you'll see that the correlation drops, and after some distance, this drops off and becomes 0. So the point where this correlation becomes 0 is decided by the length scale. Let's look at an example and confirm. So I'm going to be now drawing this covariance matrix with varying length scales. So with length scale equal to 0.05, each point has a very, very local influence on the other points. And thus, if you notice that the the covariance matrix is essentially diagonal entries 1 and the remaining entries 0. So almost the identity matrix. If we increase the length scale, you'll see that each point has little more impact on the neighboring points, and we increase the length scale to 0.5 to 1 to 2. And in the case of 4, you see that each point has a lot of relation with the other points, can influence a lot of the other points. So this is how changing the length scale will change the covariance matrix associated with the Gaussian process that we are underlying going to use. How do you think the covariance matrix will change if we change the variance parameter? Okay, so changing the variance parameter will not change the overall look of the covariance matrix. If you notice here, I'll change the variance. At the top, you'll see the variance. The only thing you need to look at is how the scale will change. So the overall covariance matrix seems to be the same, but the scale is changing, which is effectively what we would have expected, because we are now changing. This is acting as a constant being multiplied to the other part of the covariance function or kernel function. Good. So now that we've understood how the RBF kernel behaves and its different parameters, let's try and apply GP regression. I'll be creating a small dataset again, very much inspired and copied from GPS's notebook, and I'll be showing you the different trains and the test points. So the function which I use to create this dataset is 0.4 x square minus 0.15 x cube, so on and so forth. So it seems like a fairly complicated function, and I'm doing this in the domain of 0 to 5. I've marked the train points with a black cross and the test points with a magenta circle. Right? So it would be interesting to see what kind of a function or relationship we're able to now learn between y and x. This could have been really, really complicated with linear regression, but with Gaussian process regression, we hope that we'll be able to leverage the fact that the relationship between different points and the other properties of smoothness we'll be able to leverage. Okay, so let's try and do GP regression on the RBF kernel by varying the length scale. So I'll be just varying the length scale parameter. I'm assuming that this is a noiseless case. So if you remember, we had studied two cases for Gaussian processes, Gaussian process regression. One is the noiseless case, which is the ideal case, in which the function evaluation or the Gaussian process prediction at the train points must exactly pass through the train points. There is no observation noise as such. So without further ado, let's go and see what happens if we change the length scale. Okay, so this is the first case in which the length scale is set to be 0.05. And if you notice, I mentioned that since this is a noiseless case, the prediction, which is the main prediction, must pass through the train points, which is true in this case. But if you notice, everywhere else, the prediction is zeros. Now, this is because the prior that we chose on the mean was 0, and we have set a very small length scale, which means that each point has a very small influence on the other points. So that's what we end up is with this kind of a structure where wherever we have an observation, we see that we deviate from the prior, and wherever we don't have an observation, we fall back to the prior mean of 0. So there is not a lot of smoothness in this GP prediction, and as we would expect, the prediction performance is really bad. The mean absolute error in this case is 3.04. Let's increase the length scale now. Now with length scale equal to 0.25, now this looks like a slightly better prediction. Now, if you notice that wherever we don't have a lot of points, for example, between 0 and 1.8 or so, there is not a lot of points. We are again falling back close to the prior mean of 0. Similarly, after 4.8 or so, there are no other train points. So thus we again fall back to the prior mean 0. And wherever there are some continuity points, there you can see that the prediction seems fairly accurate. For example, between 4 and 5 or between 1.8 and 2.1 or so, the prediction seems to be fairly good. And this function is now much more smoother than the previous one, where the length scale was smaller. Now increasing the length scale even more, and now you see that there is a lot more smoothness to the curve now, right? But again, this suffers from the predictions being tending towards 0 after the fact there are no points after 4.8 or so, no train point. And the mean absolute error, sorry, let me not play this. The mean absolute error has been going down. Let's now increase the length scale even further. At this length scale, you see that there is a lot of smoothness, right? But it seems to be behaving very pathologically. It doesn't seem to be the case what you would have wanted, because it's beyond the train points, the prediction is extremely poor. And if we go to length scale equal to 2, something again similar, now the numbers are going to the extremities. So in a very rough sense, what is happening is we're again looking at the bias variance trade-off. Initially, there was a very high amount of bias. The model was severely underfitting. And after that, we see a high amount of, oh, sorry, it's the other way around. So if we go back. So in this case, there is really poor predictions. And if we go down further, we keep on adding more smoothness, but then we keep on adding a lot of variance also. As we change a few points, our predictions can change a lot. Now that we've seen the case for when we assume the noiseless case, let's now look at the case where we assume that the observations could be noisy. So you don't fit perfectly to the train points. If you notice here, at each of the train points, we are not fitting very well, which means that the prediction is in some noise range. Right? Let's try and increase the lens scale to see how the prediction happens. So now this looks like a fairly good prediction with lens scale 0.25, but we are still missing on a lot of the points. Increasing the lens scale even more makes the curve even more smoother. This, I would imagine, being a reasonably good estimation. And so would this be with lens scale 1 and lens scale 2 now. As you keep on increasing the lens scale, your curve will keep on getting very, very smooth. As you have a very low lens scale, the curve will be very, so there'll be a lot of local properties. So there'll be a lot of local properties, and you'll also see that your predictions would be mostly tending towards the prior mean, given that we don't have a lot of points. If we had a lot of points, then this would have been a different story. And increasing the lens scale keeps on making a very smooth curve because each point is now related with even farther away points. But thus far, we had set some kernel parameters and we were just trying to visualize the GP regression based on those parameters. So, like we did in the case of linear regression, could we learn these parameters which are responsible for the covariance function, the covariance matrix? Now, this seems like a slightly odd idea because what I'm proposing is to learn the parameters of what is supposedly the prior. But this is done in practice. And let's try and optimize the kernel parameters again using the excellent GPy library. I have done this. I've optimized the kernel parameters on the train set. And if you notice now, the parameters that I've ended up learning are the following. High amount of variance, 12.4 is the variance factor, the lens scale is 2.34, and the noise variance is 0.017. So which means that this is still fairly close to the noiseless case. Now let's try to visualize this function that we have learned based on. So let's do the GP regression based on the kernel parameters that we have learned. And if you notice, this seems like a fairly good estimate. So which is surprising also in if you've just been exposed to parametric models. So given this really small amount of data also, we've been able to fit in a fairly good model. But this was still not very difficult because a lot of the assumptions that we would have made regarding smoothness, etc., were very valid in this case. And if you notice, the mean absolute error on the test set is 0.126, which is fairly good. We have seen the RBF kernel. There are many other kernels which could be used. I'll not dive into all of them, but I'll just show an example of one other kernel, which is the periodic kernel. And then we'll see how to combine two kernels. So let's look at the periodic kernel, and I'll again, as I'd done earlier, I am plotting the kernel function evaluation between 0 and the other points on this axis. So all the points from -4 to +4, I'm evaluating the kernel, like I'm plotting the kernel function evaluation between these points and 0. And if you notice that there is a periodic element to it, and the periodic element is, so we have so at -1 and +1, the curve seems to be exactly the same. So at the same point, which matches what we had said that the period is said to be 2. So this will end up in creating a covariance matrix where after the same distance in this case, which is the period, you will have the repeated function evaluation values. So let's now try to use this kernel and learn its optimum set of parameters and fit to the previous regression task that we had, the data that we had. I have done exactly that. As expected, you'll see that the fit is not very good because the fit is will try to get will try to predict in a way where the data seems to show periodic behavior. While there is some notion of periodic behavior there, it's not very strong, right? So just using the periodic kernel here does not seem to be a very good choice. I'll now create another dataset where the periodic kernel would be much more useful. So I've created a simple dataset where I have the true function as sine of 6x plus 0.5 times cosine of x. And I've added some random noise to it. And if you view this function, then it looks like the following. Now, just looking at this scatter plot makes it extremely hard to understand what the ground truth function is. Let's see what a GP can learn. Now, the kernel that I've given to the GP is this kernel K, which is the periodic kernel with the period of 2, and I'm learning its optimum set of parameters. So let's see what we learn. Once we optimize, we are able to learn the optimum set of parameters learned are the period learned is 1.63, the variance learned is 19.2, the length scale learned is 1.9, and the Gaussian noise learned is 1.66. Let's try and now plot this on our data. On this new data, it again does not look very good. Okay, I think I've made a small mistake here. Instead of plotting this on test x and test x2, we should have done this on, instead of plotting this on test x and test x2, we should have learned it on that train x2 and test train y2. It seems that I've not defined these yet. Train x2 and train y2. If I look at the parameters learned, variance, length scale, and Gaussian noise. So it seems that I'm not using the right kernel here. Let me just run this again. Okay, so on this data set, okay, so now the period that I've learned is 2.04, the variance is 1.62, and the Gaussian noise is the following. I'll be using plotting on test x2 and test y2. Let's see. Okay, so it seems to be picking up some of the points. Now, at train points, it is able to, of course, pick up because the noise variance learned in the so this is almost close to the noiseless case because the Gaussian noise variance parameter is almost close to 0. So you notice that it's not doing a very, very bad job. Maybe if it had some more power to it, maybe it had, two periodic kernels or a multiplication or some combination of periodic kernels, it could have done a far better job. So what I'll now show here is I'll be looking at two kernels. The first kernel is a periodic kernel, and the second kernel is an RBF kernel, which we've been seeing thus far. I'm using two different combinations. The first is K1 plus K2. The second is K1 into K2. Both of these are valid kernels. We are not going into the theory of what constitutes a valid kernel, but just let's remember that combining the standard kernels, it will also give a will also give a valid kernel. So let's first also try to make the plot that we're making above with these new two kernel functions where we're trying to evaluate the combined kernel functions. So in this plot, you might see that so we initially had the RBF kernel, which is shown in this orange curve, and the periodic kernel is shown in this blue curve. And I'm showing two different combinations. One is periodic plus RBF, which makes sense. So this is just addition of the orange curve and the blue curve, giving us the green curve. And we also have a periodic into RBF, which is given by this red curve. So that's a multiplication of these two kernels. And we can similarly also try and visualize the covariance matrix. So if we do RBF plus periodic, you'll see that after every some period, which is away from every point, there is some correlation between that point and the base point. Right? So this is RBF into periodic. This shows characteristics of both RBF and periodic. And similarly, RBF into periodic will also show the characteristics of both. But since RBF tends to um, tends to ensure that there is not a lot of correlation in faraway points. So that is why the periodic element is fairly narrow in this case. You don't see a lot of periodicity apparent in this data. So what you could do is to now combine these different kernels, and we could plot them. We could plot for either train dataset 1 or train dataset 2. Let me do this for the train dataset 2. And let's see, which was the new dataset which we created, which was a sinusoid plus a cosine. So here you see that with this new kernel function, it's again doing a reasonably good job, not a very good job. And the combined two is the combined one kernel was, let's see, combined one was RBF plus periodic, the second one was RBF into periodic. So let's try and look at RBF into periodic function now. I'll do this for the second data set. Okay, so this seems slightly odd, right? But this is not very odd. What this is telling us that it's extremely hard for this particular GP, given the kernel that we have, to predict anything else than just zeros. So this seems a little odd, but sometimes we do end up in situations like this. So what we can also do is to just print m to see the values that we get. So we get the variance in the periodic to be 0.016, the period to be 5. And notice we're going on a scale of 0 to 5 anyway, so a period of 5 over here does not add a lot of significance. The length scale chosen by the model to optimize set of parameters is 13. So if you increase the length scale, then you'll end up with a very, very smooth function. And the smoothest function you can get is just a straight line. Right? And the variance on the length scale learned in the RBF is also, the length scale learned in the RBF is also pretty high. Right. So having demonstrated GP regression for 1D data, now I'll be demonstrating it for two-dimensional data. I have created this two-dimensional data here. So we have two axes and x and y, or two dimensions x1 and x2, and we have different points, and the radius of this point is denoting the value. So for example, we have 3, 4, so x equal to 3, y is equal to 4. Corresponding the value is, this is 1, 2, 3, 4.1, 2, 3, 4.2, right? And we also have the smallest point, 3, 1. So at x equal to 3, y equal to 1, we have the value 0.5. Right? So these are the set of values. What we're trying to learn is now our 2D Gaussian. So let's see how the, for 2D, we will be using GP regression in 2 dimensions to visualize the GP regression. So what I'll be doing is to now use a kernel with an RBF kernel which accepts its 2 dimensional input. And I've just kept the length scale to 1 for now. And I've fitted in the regression model, GP regression model on this data set. And if you remember that whenever we have to do contour plots or surface plots, we want to get an estimate at each of the grid points. So we want to get an estimate at 1, 1.1, so on and so forth, depending on how many divisions we do on this grid. So I've just created that that division amongst on the two axes, and I've used the mesh grid function, and finally I've predicted for each value of on this grid. I predicted what's the predicted mean that is I've obtained here, and I've made a contour plot of the prediction. So if you notice that what this GP regression is suggesting is that points close to x equal to 2 and y equal to 2 are the points where the value is maximum, and then you keep on reducing the values, and the points in this part of the region, this circular region, are also fairly low in magnitude, so you can see the different contours. We could have also obtained a 3D surface plot for the same, and this also gives you a nice understanding of what is the function being estimated. Now this does not seem very difficult to understand, given that you see, so there are quite a few points here in the middle where the values are high. So think of it as you want to fit a very smooth surface which would either pass through all of these points or be fairly close to these points. So if you want to learn a smooth surface, you'll end up with the kind of contour plot of the surface plot that we're seeing here. So in the vicinity of x equal to 2 and y equal to 2, you'll see that the values are high. And in this part, which is one dimension is 2, the other dimension is 5. Right? So okay, so around this point, we see that there is a depression. So all of the values are fairly small. Right? So that is the kind of surface plot that we'll be able to predict. But we also get a variance at each point. We just don't get the mean prediction. So this is something we've been doing earlier also. So if you notice, we just look at this plot. So we don't just get the mean estimate. We also get the confidence interval, because effectively what we're learning is a high dimensional Gaussian. So we can very easily plot at each point that what is the variance. So here what I've plotted is the variance for this data set, variance and prediction on this data set. And if you notice, this is interesting because this is showing that the variance is very high on the extremities, and the variance is very close in the center part where there are a lot of observations in them. So this is something which occurs very frequently in Gaussian process literature, that you'll generally have a lot of uncertainty around the extremities. This was also happening earlier in the 1D case. So if we go back up, right, so you see that there is a lot of uncertainty on the extremities because we don't have a lot of points. And we also saw this for the case of, let's look at look at the amount of uncertainty or the deviation in values you see around the extremities. This could be a problem and something we need to think about. I'll finally come to a real world application. I'll be looking at the air quality data from Delhi over different points. So basically different points means different latitude and longitude, and I'll be looking at the PM2.5 concentration. And I'll be trying to estimate the PM2.5 concentration over the entire region Delhi. So there are only about 20 odd stations, air quality stations in Delhi, but we want to estimate the air quality at all of the other places which are, let's say, not very close to these air quality monitors. So in a previous post, I had written about how to get the air quality data for Delhi or using good public APIs. And I've also mentioned a source for downloading the shape file of Delhi, so which is useful for plotting the map boundaries, etc. This is how my dataset looks like. For each latitude and longitude, I have the corresponding PM2.5 values. This is now data for one particular day, which is just one particular day, and uh, the mean PM2.5 for that day. So this is I'm using GeoPandas and I'm plotting the different points. It does not seem to does seem slightly difficult to understand, but I've created now a function which visualizes in 2D the output of the GP regression. So what we have to do is to first pass in the 2D data, which I'm passing in the form of longitude, comma latitude, and the corresponding y value, which is df of value. I'm passing in the kernel, and I'm just optimizing the kernel parameters. And then, as we've done before, since we need to draw the contour plot, we need each of the element in the grid, for which we use the mesh grid function. And I then make a prediction for each of these points, right? Which I do using this line where I'm just calling predict noiseless. What I'm also doing in this particular function is to read the shapefile, which contains the boundaries for the city of Delhi or the Union Territory of Delhi, and I'm also going to be plotting that. So just to give the figure a more contextual understanding, I'm also then plotting the different points corresponding to the different locations where we have the monitors. And what I'm doing here is to show you all the different kinds of kernel combinations that I've looked at. The first kernel I've looked at is a simple two-dimensional RBF kernel. The second kernel is a product of an RBF kernel with another RBF kernel. The third kernel is the sum of an RBF kernel plus the previous kernel, which the previous kernel was a product of two kernels. The next kernel I've showed here is a Matten kernel. So Matten kernels are very popular in Gaussian process regression. There are I'm showing here two variants to this Matten kernel, and I've then created another complex looking kernel, which is a combination of these Matten kernels and the RBF kernel. And finally, what I've done is to show you the visualization. So first let's just look at the visualization for the first kernel, which is just a two-dimensional RBF kernel which I'm using. So if you can see, this is in the background showing the map of Delhi. Of course, it's unfortunately the map is not fully correct. So it's ended up not showing a few territories as a part of the Delhi, and these circular dots in the legend are showing the ground truth PM2.5 pollution at these different locations, and this scale is showing us the color scale for the prediction of the GP. I'm using a purple CMAP, so we'll be going from white indicating minimum to dark purple indicating the maximum. Now, if you notice carefully in the ground truth, we have values ranging from fairly low to so ranging from let's say 46 to 265. But the color bar that we've seen here is just going from 158 to 159. Now, this does not seem to be a very good prediction. And if you think about it, this is effectively trying to create a mean prediction. So the prediction is something like the mean of the dataset at each of the points. At the top of each plot, I'm also showing the objective which is computed. So we compute an objective. There is an objective function which we try to optimize in order to learn the kernel parameters. I'll Let me now show you the evaluation for the Matten 3.2 kernel. So this also seems to be fairly similar. Now, if you see that the prediction is fairly close to just the mean, so I would say this is not a very good prediction. We would ideally want some predictions where we have much finer grained maps. Matin 5.2 also in this particular case does not yield a lot of value to us. So this kernel seems to be doing something more interesting now because the range at least is going from 92 to 188. This is the kernel where we have RBF into RBF. And this is the kernel which I was most happy to look at. Although I've still not done the evaluation in terms of um, the RMS error. But here at least you're able to see some zones. You're able to see some better patterns, and not just a single radial pattern. And you also see on the scale that there is quite amount of deviation, going from 32 to all the way to around 240 or so. Right? So at least it's able to pick up the range of values correctly. The next kernel which I've done is doing a really bad job. So here you're just predicting between 0 and 4. So this is the case where the prior, where the mean 0, ends up very clearly dominating, and you're not even able to get any reasonable amount of prediction. So it's a case where GP is not behaving well. So I hope you got some idea of how to use Gaussian process regression in the real world, and you would give this a spin.